Hello everyone, my name is Nina Rodriguez, and today I'm going to present a couple topics to you. One of the probably first topics you ever learn in chemistry is what matter is. So let's get started. So matter, as you see on my screen, matter is broken up into two different topics. You have, on one side, you have substances, and it breaks down even further, and the other side you have mixtures. I'm going to stick to the substance size first. So in substances, you have elements and compounds. And elements, as you see the definitions over here, they are the building blocks of matter. They are what matter is made out of. Okay, so you cannot decompose this. You can't break it down any further. It is a single type of atom. And we have 118 known elements as of today, and who knows how many more will come. Each one either has like a 1 or 2 letter symbol, like I'm sure you've seen like hydrogen as H or oxygen as O. We all know certain elements out there in the world. And you also can take 2 or more different elements and chemically, as you see right here on the flow chart, chemically combine them to make compounds. We come into compounds more than we do of elements, like water and salt and sugar. We come into contact with those all the time. But for example, like metals and nonmetals, sodium chloride, ionic bonding, if nonmetals and nonmetals bond with each other, then you would get like carbon dioxide, water, sugar, as I mentioned. And these compounds, they have completely different properties than what the elements were originally made out of. Like H is a gas and oxygen's a gas, but when you chemically put that H and that O together, then you get water, okay? And water definitely has different properties than hydrogen gas and oxygen gas. So the original elements, they have their own distinct properties, and as you chemically combine these elements together to make a compound, you have a different set of properties. So that's what we mean on this flow chart as a chemical reaction has occurred. On the next slide, we have different types of mixtures, okay? And we come into contact with these too. So mixtures can be broken down to homogeneous versus heterogeneous. Now, homogeneous mixtures are uniform compositions throughout. You cannot see any type of distinct layers in it, like no floaties or chunks. You don't see like one liquid sitting on top of a different liquid. You see no distinct, any type of different properties about it. And you actually, you may even need a microscope or something like that to actually see maybe something even smaller, but your physical eyes cannot see any distinct, different characteristics about it. So we like to call these solutions. So like when salt and water, when you put like some salt in some water, if you're going to boil some water, I can't see the salt, and I can't see a difference between the salt versus the water versus just regular tap water. I can't see the difference between it. Now, microscopically, that's a whole nother story, but I can't see it distinct. But if I were to put like heterogeneous type of a topic, heterogeneous have separate distinct regions or layers. Like if you put oil and water together, oil and water do not mix with each other. And that's a different topic in chemistry called polar and nonpolar. But because I can actually see the oil on top and the water on the bottom, I can actually see 2 different regions that are in that mixture. Or like as you see in the PowerPoint, like a chocolate chip cookie. I could see the cookie, I could see the chocolate pieces, maybe you could see like some walnut pieces in it too. I can actually physically see those type of distinctions. So that is the huge difference between a homogeneous and a heterogeneous type of mixture. And as you see right here, every homogeneous mixture is called a solution, okay? So in here, let's do a couple examples. So if you had to classify each of the following as either an element or a compound or a mixture, but if it is a mixture, what type of distinction between it as in homogeneous or heterogeneous? So like helium, for example. Well, I know helium as a gas, and as you see the picture down here at the bottom, and we know helium in balloons, okay, but helium's an element, okay, it's one of those naturally occurring elements, so I'm going to put a big old E right next to that because I know it's an element. Nitrogen, that gas that's surrounding us in that atmosphere, 80% of the atmosphere is nitrogen, and I know nitrogen, very important element in our atmosphere, and definitely very important to our plant life and animal life too. Pure water. Now, there is a distinction between pure water and tap water, okay? And we'll go a little bit more further in that when we go through the PowerPoint. But pure water, as in H2O, well, I know H2O, I see some hydrogen and I see some oxygen, and those are two different elements. Well, if I chemically combine those two elements together, then I can make a compound. So pure water would be a compound, and I'll just put it right over here. Pure table salt, and I even try to give you a hint here, Mr. Sodium chloride, okay? And I know we haven't talked about how to write formulas yet, but sodium chloride, sodium's an element, chloride is an element, and when they chemically combine together, you make salt. And we will, as we go through this process, I will show video clips of how stuff come about, like sodium chloride, the reaction for that. It's a very kind of violent reaction, but it's very cool. And we eat table salt all the time. So sodium chloride is also a compound. Now Coca-Cola, as you see a picture right here, Coca-Cola, I don't see any distinct layers in it. I definitely don't see any floaties in it. Now you do have some bubbles in there, and that's okay. The bubbles could be a kind of a distinction, maybe it could be heterogeneous, but Coca-Cola as a solution is a homogeneous solution. Okay, and I'm just going to abbreviate here because I'm a little bit out of space. Air is definitely made of many type of elements and compounds. I mean, air, we obviously know some oxygen, we know some nitrogen, we definitely have some carbon dioxide going on out there. We even have like other gases like argon, some neon gases. Air is actually made up of probably like 20 different elements and compounds, and because it's a blend of elements and compounds, we call that also homogeneous. Okay. Now I know you're probably thinking of like, what about the smog level that you see? Like if you were going to stare at the top of like the San Bernardino Mountains and look down onto the city, you probably like see like this very thick layer of stuff. Well, obviously then you kind of get like a heterogeneous type of distinction, but we're just talking about pure air. And fruitcake, not a lot of people know what fruitcake is, but I put a picture on here so that you'd know. Fruitcake is usually made around like holiday times, Christmas time, and it's basically like a bread that kind of has like little candies put in it, like little jelly candies in it. And as you see in this picture, I could see obviously the bread layer. I can even see the crust layer. I mean, even if I would have put the word bread on here, bread is definitely heterogeneous because I can see a distinction between the inside, the squishy kind of layer, versus on the outside, the crust layer. But I also see the individual candies that make up that fruitcake also. So definitely heterogeneous. Okay. All right. So hopefully that gives you some clarification between the differences between elements and compounds and mixtures. Okay. And I'm going to lead into my next topic of physical and chemical changes. Now, the first thing is, before we get to the changes, let's talk a little bit about properties. Okay, so I put some definitions up here. A property allows us to recognize a particular type of matter and distinguish it from other types of matter. So there is a difference between physical versus chemical. So physical property is more of like an observation. The sky is blue. The sock has an odor to it. The density of water, 1 gram per mil. The wood is hard, or the solubility, the sugar dissolves in water. You're not really changing anything about it. It's still water, it's still a sock, it's still a piece of wood, it's still the sky. You haven't changed anything about it. Okay. Melting point is basically the temperature that something melts. Well, it's still that same substance, but it just melted. Same thing with boiling point, the temperature at which something boils. But if you have a chemical property, and a chemical property, this is actually, it's a distinction that it can react and maybe produce something else. Like if anything reacts with acids and bases, they usually have a distinct different type of property that they would produce. Like if I took like a piece of metal and put some acid on it, well, I'm definitely doing something to that metal, because I guarantee you that metal's not going to be the same. So if the actual substance of what it's comprised of changes chemically, then that's a chemical property. Okay, it can actually change into a new substance. Okay, So I also wanted to break down a couple other properties we talk about in chemistry, intensive versus extensive. Now, they sound kind of a little the same, but there is a distinction about it, and it has to do with that thing called quantity, but an amount quantity. So with intensive property, it doesn't depend on the amount of the substance, okay? Like temperature. Temperature is a measurement with a thermometer, okay? It's not like I put on a balance, or I can't put it in the graduated cylinder or something like that. It's not an amount, it's a measurement. But with extensive properties, it actually does depend on the quantity. Like if I put a piece of gold on a balance and I say that's 10 grams, that is the amount of that piece of gold. And if I took a different piece of gold and weighed that, maybe it's like 20 grams. So it actually depends on an actual set quantity. So I put on there some mass, volume, as in when you use like beakers and graduated cylinders, okay? So on here, kind of a little example. Let's say you are boiling some water, okay, and you see some bubbles rise to the top of the container, okay, or the pot, whatever you're boiling the water in. Now, what's inside those bubbles? Well, all I have in my pot here is just water, okay? And then when I start to see bubbles, and the bubbles go from the bottom to the top, and what is in those bubbles? Well, it's still water, okay? I didn't have anything else that was in this pot besides just water. So I'm taking those liquid water, okay? So the little abbreviation for liquid is a little L, and I'm changing by adding some heat, okay? And usually the symbol for heat in chemistry is a triangle. And I'm taking that water and making it into a gas form, and we call that vapor. So students like to think that maybe I created something new, like maybe I created some oxygen or some hydrogen, okay? I didn't decompose it. I'm just boiling the water, okay? Or if I maybe added like some electricity to it, like electrolysis, then I can break it down. But I'm just taking the water that was the liquid and boiling it and just changing the state of matter. And anytime you change the state of matter, that's a physical change. Because remember the distinction between it. A physical change is you did not change what the material was made out of. You just changed the way it looks. And I just took water as a liquid and changed it into a gas. Okay? So I have now physical versus chemical change. So now we're going to actually do some changing. Okay? So if the physical state of matter is altered, but the chemical composition remains the same. So when we say chemical composition, we mean what it's made out of. If that doesn't change, that's just a physical change. I took this pen and I did a reaction with it, and now this black pen turned to red. Well, that's a color change, okay? And this is where it gets a little crazy with color, because if I just say this pen is black, that's a physical property. But if I actually do a change in color, color is a very hard one for students because they still think it's a pen, but when it comes to like color change, it's more of a chemical reaction. And I'll explain why. Probably the pen is probably not the greatest example, but if I would have took maybe some copper sulfate. Copper sulfate are these beautiful blue crystals, and if I heat them up, well, what happens is those copper sulfate have some water in it, and what happens is when you heat it up, those crystals will change from blue to white. Now, it's not copper sulfate no more because I did a chemical process to it. I drove off the water. And because I drove off that water, I don't have water no more. So it changes color from blue to white. And you guys would see this in a chemistry lab. It's usually a common lab that teachers do with their students. So if I don't change the chemical composition of it, then it's just a physical change. But if I actually alter what the substance is made out of, it's not hydrogen no more. It's not oxygen no more. It's water. That's a chemical change. Okay? So as you see the two different distinctions between the definition. A chemical change requires that a new substance is formed, and it's a completely different composition than what it originally was made out of. And like I said, be very careful with color changes, because depending on how they state it, obviously if this pen is black and went red, it's still a pen. I didn't change anything about the pen. But if I did an actual piece of wood and I burned it, then obviously I have a chemical change because it's not wood anymore. And you would see obviously a color change. You would see smoke appear. You would see ashes formed, and so forth, so forth. So I put some examples on here that we can go through. And if you want to take a minute to pause and go through them first, and then check your answers right now, okay? Baking soda reacts with vinegar to produce carbon dioxide. Well, I can see right there definitely. I started with baking soda and I had some vinegar, and now I produce carbon dioxide. I produce something completely new. So obviously that would be a chemical change. And I'm just going to abbreviate physical versus chemical. Copper coating on the Statue of Liberty turns green. Now, this is a good one. The copper, originally the Statue of Liberty, when it came over, looks like a brand new copper penny, okay? But the problem is what happens over time, especially with metals like copper, they react with oxygen. And because they react with oxygen, there's a chemical reaction that happens, and I actually produce a new compound called copper oxide. And what happens is that Statue of Liberty that we're all used to seeing, that greenish color, that actually was a chemical change that happened because over time, metals, they do tarnish, they do rust, and you do see a different type of color change. Like a penny does it, jewelry does it. Okay, I'm sure you've all seen different type of metals out there that have changed color. And it's because it's reacting with oxygen. Okay, iron does it a lot too. It creates rust. So this is definitely a chemical change. The addition of salt melts ice on the highway. Okay, so I'm just taking ice, that's a solid, and I'm melting the ice. So I'm taking solid ice and making it into a liquid ice. Still water, okay? I didn't change the composition of water, so that's a physical change. Steam condenses on a window pane. So like in the morning, if you see like a little bit of water drops on your windshield, so I got steam, so I'm talking about water as a gas. And it condenses, okay, so we got a temperature change happening there. It's lowering the temperature, and I'm just going to take that water and make liquid water. Still got water. I didn't change the composition of water, so we got a physical change. Now, epoxy resin, if you're not familiar with it, you don't really need to know much about it, but I said it cures and it hardens. So maybe it actually was a liquid and it hardened, so maybe it turned into a solid, okay? Definitely, I still have the same original substance. I didn't create anything new. So definitely a physical change. Sugar dissolves in a cup of coffee. Okay, so you take that sugar, you dissolve it in a cup of coffee. I didn't create anything new. I just got sugar coffee. Okay, that's all it is. So definitely a physical change. And before you probably think about, well, how are you going to get that sugar out of the coffee? Well, you can. And there's an actual process when we talk about physical methods of separation. You're going to learn about filtration, distillation, chromatography, crystallization. And crystallization is a way that you can actually get that sugar out of the coffee. It's very cool to see. Natural gas, so natural gas is methane, CH4, and it burns. And anytime we burn something, it means we're adding some oxygen to it. And what happens is when you take a gas and react with oxygen, you definitely produce something new. And most of the time, it's carbon dioxide and water, okay? So I don't expect you to know a lot of what they produce, but just knowing that it produces something new means it's a chemical change. If I have a piece of aluminum metal, so kind of think like your aluminum foil that's in your kitchen, and if I said corrosion, well, that aluminum, okay, is basically just being kind of surrounded by that oxygen, and over time, that aluminum will change. And you're going to produce a compound called aluminum oxide. So definitely corrosion, think of it like rusting, okay? Corrosion is a chemical change. Melting ice, okay, kind of have a little repeat up here on this third one. So melting ice, definitely you have that solid water and we are melting it. So I'm going to that liquid phase. So definitely still a physical change. And a couple others on here too. If you want to pause it, try some first and then check your answers. You're more than welcome to. Pulverizing aspirin, so basically taking like a little aspirin pill and kind of like just smushing it. Okay, I still got aspirin, now I just got powdered aspirin. So definitely a physical change. Digesting a candy bar. So think about it. You take a bite of that Reese's Pieces or that Snickers bar and you consume it, you eat it, you know it's doing a reaction in your stomach. You got the acid eating away and you know it doesn't look the same way as it comes out. So it's definitely a chemical change. Sorry, I got a little gross there, but it kind of helps to think about, I have a totally different composition. Explosion of nitroglycerin, definitely, I think that keyword explosion, kaboom, fireworks, anything to that effect, definitely a chemical change. I definitely don't have nitroglycerin again. Milk turning sour, okay, what happens is over time, you know, your milk in the fridge doesn't stay in that perfect condition. It eventually expires, and what happens is the more and more you drink the milk, you get this layer of air that sits on top of it, and that air and milk, they do a little reaction back and forth, and that souring is definitely a chemical change. Okay, oops, hello, definitely a chemical change. Burning paper, I light paper on fire. I don't got paper no more. I've completely changed the composition of paper. I got ash, okay, and ash is definitely something else. That's just pure carbon. So burning paper is definitely a chemical change. Forming a frost on a cold night, okay, so you definitely, that frost, okay, kind of think of it like that snow, that solid water, and I'm just taking those molecules of water that are in the sky, the air, and I'm just creating like a little film of frost. So definitely a physical change. Bleaching of hair with hydrogen peroxide. Okay, this is the key one too, because one, bleaching, you put bleach in your hair, you got definitely a chemical reaction going. And the hydrogen peroxide, when you bleach, it will do a color change. So if you got dark hair, it will definitely go blonde. And you know, if you've ever dyed your hair or bleached your hair, you can't get that color back. So what do you have to do over time? You got to let the hair grow out and or cut it or so forth. But definitely a chemical change happens there. And copper wire is hammered flat. Well, I just took a piece of copper wire and I just flattened that piece of copper. Still got copper. So a physical change. Okay. So hopefully, ladies and gentlemen, this helped you with what matter is all about. In later discussions, we will go more in depth with matter, but I want to give you a little generalization of the difference between elements, compounds, mixtures, and a little help with physical and chemical changes and properties. Hope this helped you. See you next time.